Paragi Joshi. In today's video, we are going to solve some important questions of theory of computation. So let us proceed. So we have our first question here. The question states that use this set of productions to show that each of these sentences is a valid sentence. And we are given 4 different sentences. Okay, the first sub question we have is the happy hare runs. According to the production rule, a valid sentence is a sentence which have 2 subparts, that is a noun phrase and an intransitive verb phrase. Within noun phrase, we have 3 subparts, article, adjective and noun. And with intransitive verb phrase, we have 3 subparts, intransitive verb. So according to the sentence, we have article is equals to the, adjective is happy, noun is hare, and transitive verb is run. So the happy hare run is a valid sentence. The second sub problem we have is the sleepy tortoise runs quickly. Now, according to the production rules, we must have 2 subparts, that is a noun phrase and intransitive verb phrase. Within noun phrase, we should have article, adjective and noun, and within intransitive verb phrase, we should have intransitive verb or an adverb. Now, according to the sentence, the article here is the, adjective here is sleepy, noun here is tortoise, intransitive verb is run, and adverb is quickly. So this is a valid sentence. The third sentence we have is the tortoise passes the hare. Now here the noun phrase should include article and noun, and in the sentence the article is the and the noun is tortoise. And intransitive verb phrase, it should be intransitive verb, and here in the sentence the intransitive verb is passes. In the noun phrase again the article and noun are the and hare, so it is also a valid sentence. And in the fourth sentence, the sleepy hare passes the happy tortoise. The is article, sleepy is the adjective, hare is again the noun, and passes is the intransitive verb. Again the is the article, happy is the adjective, and tortoise is the noun. So it is also a valid sentence. So now let us proceed to the next question. Question number 2. It states that construct a derivation tree for the sentences in the given question. The first sentence we have is happy hare runs. It is almost similar to the first question. Here only we have to draw a tree for the given sentence. Our tree must include 2 subparts, that are noun phrase and intransitive verb phrase. According to the production rules, if a sentence includes both of these subparts, then the sentence is a valid sentence. So we already know here the sentence is already a valid sentence, as we have seen it in the first question. The is the noun, happy is the adjective, and hare is the noun again. Intransitive verb here is runs. The derivation tree is already present on the screen. Okay, so the derivation tree for the second sentence, the tortoise passes the hare, we have already on the screen, and here the noun phrase are the and tortoise. The intransitive verb phrase in the between is the passes, and again the noun phrase which include article and noun are the and hare, and the derivation tree is already on the screen. You can see and refer to it. The third sentence is sleepy tortoise runs quickly. Here the derivation tree will include noun phrase and intransitive verb phrase again. The sleepy and the tortoise are the article, adjective and the noun of the sentences, whereas intransitive verb and adverb are runs and quickly. So it is a valid sentence, and the derivation tree is already on the screen. Okay, now let us proceed to the question number 3. The question number 3 states that we have to construct a phase structured grammar that generates all the signed decimal numbers, consisting of a sign, either positive or a negative, a non-negative integer, and a decimal fraction, that is either the empty string or a decimal point followed by a positive integer, where initial zeros in an integers are allowed. So let us see how we can actually solve the question. So here we can see S can be either a string or a sentence. S can be signed integer or an unsigned integer. S can be a sentence or a string, signed integer or a positive integer. Sign can be positive, sign can be negative. Integer can be a digit, or an integer can be an integer, or as well as digit. Digits from 1 to 9 are allowed, as well as 0 is also allowed. Positive integer can be an integer or a non-zero digit. Positive integer can be a non-zero digit, or similarly an integer. Positive integer is also a non-zero digit. Non-zero digits are allowed from 1 to 9. Problem of this question states that we have to provide a Backus norm form for the given grammar. So here again we can have signed decimal number. It can either be a signed integer or a positive signed integer. Sign can be either a positive or a negative. Integer can be a digit or an integer digit. Digit can be from 0 to 9. Non-zero digits should be from 1 to 9 obviously. Positive integer should be integer or a non-zero digit. It can also be a non-zero digit and integer, and at last it can be an integer. Non-zero integer and non-zero digit. Another sub problem we have is we have to construct a derivation tree for -109 for the given grammar. Now in the derivation tree we should divide a signed integer into a signed integer or a digit. Sub parts of the derivation tree should be a signed, digit or an integer. Here the derivation tree of the given -109 number, signed integer can be subdivided into a sign and an integer. Sign must be negative. Then an integer should be divided into a digit and an integer. Here the digit would be 1. An integer then sub would be divided by a digit and an integer, and at last we would have -109 as a sign, digit and digit. The derivation tree for the next question is -314. As we can see, it is a signed decimal integer because 3.14 is a decimal number. Number would be further divided into a sign and an integer, the decimal point in between, and at last the positive integer. The sign would already be negative. Integer would be subdivided into the integer and digit again, and the digit we will obtain would be 3 and 1. Then the positive integer would be further divided into a non-zero digit, that would be 4. So here is the derivation tree of -314. So now let us proceed to the question number 4. Question number 4 state that give the production rule in Backus norm form for an identifier if it can consist of. We have some problems given as A. One or more lowercase letters. So here the identifier can have one or more lowercase letter, that is a lowercase letter 1 or more than 1, and lowercase letter would obviously be from A to Z, that is lowercase English letters. The second sub part is at least 3 but more than 6 lowercase letters, no more than 6 lowercase letters. So identifier can have 3 lowercase letters but it should be less than 6 or equal to 6. So identifier can have 3 or 4 or 5 or 6 lowercase letters, and lowercase letters would be from A to Z. So in the third sub problem, we must have 1 to 6 uppercase or lowercase letters beginning with an uppercase letter. This states that the beginning letter, the first letter, should be an uppercase letter. So in the solution, the identifier can have uppercase letters from 1, 2, 3, 4 or 5 or 6, and the beginning letter must be an uppercase letter, and the rest can be lowercase or either uppercase, and the letters should be from A to Z lowercase, and it also should have A to Z uppercase letters. The fourth sub problem states that the identifier should have a lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric characters. Lowercase or uppercase letters and digits are also allowed. So in the solution we can see that an identifier here should have a lowercase letter in the beginning, that it should be followed by a digit, or then it should be followed by 3 alphanumeric letter, or again the letter, the digit and 4 alphanumeric characters. Digits can be digits, alphanumeric can be letter or digit, letters can be lowercase or uppercase. Lowercase letters should be from A to Z, uppercase letter should be from A to Z, and digit should be from 0 to 9. So now let us proceed to the question number 5. The question number 5 states that give production rule in Backus norm form that generates all the identifier in C programming language. In C, identifier starts with a letter or an underscore that is followed by one or more lowercase letters or uppercase letters, underscore and digit. From the question, we can understand that in C programming language, we have to design an identifier, and they have stated some rules according to which the identifier should be made. In the solution, we can see that identifier can be letters and identifier can be a symbol, that is underscore. Letters can be letter, symbol can be letters or digit. Letters can be uppercase or lowercase. Letters should be from A to Z, uppercase or lowercase. Digit should be from 0 to 9. So now let us proceed to question number 6. The question number 6 states that give the production rule in extended Backus-Naur form that generate all decimal numerals consisting of an optional sign, a non-negative integer, and a decimal fraction, that is either the empty string or a decimal point, followed by an optional positive integer. Optionally proceed by some number of zeros. So now let us see how to solve this question. So in this question we have to construct a numeral that can be consist of an optional sign, that is either a positive sign or a negative sign, then a non-negative integer, and a decimal fraction that can either be an empty string or a decimal point, and it then must be followed by some optional positive integer, optionally preceded by some number of zeros. So in the answer we can see then sign and non-zero digit or a decimal, then again sign or a decimal. Sign can be positive or negative, non-zero digit should be from 0 1 to 9, sorry, not 0, and digit can be 0 or a non-zero digit, decimal can be digits. Okay, so let us proceed to question number 7. Question number 7 states that give the production rule an extended Backus-Naur form for identifiers in the C programming language. In this question, we have to construct an identifier in C programming language according to extended Backus-Naur form. As we already know, in C programming language, identifier starts with a letter or an underscore, that is a symbol, and is further followed by lowercase or uppercase letters, underscores, and digits. So in the solution we can see that according to extended Backus-Naur form, identifier can either be a letterless symbol or letterless. Letters can be a letter, symbol can be letters or digit. Letter can be lowercase or uppercase letters. Lowercase letters and uppercase letters should be from A to Z, and digit should be from 0 to 9. Okay, now let us proceed to the next question, that is question number 8. For each of these strings, determine whether it is generated by the grammar given for postfix notations. If it is, find the steps used to generate the string. So in the question we have given some strings and we have to determine whether it is generated by the grammar given for postfix notations. So let us see how we can do that. The given in the string in the question is ABC, a star, and the plus operator. So the whole string given is represented as an expression. An expression can be further divided into term and an add operator. Add operator is represented by add symbol. Then the term can be further divided into factor, and a multiply operator and an add operator. And then again it is further divided into an identifier. Identifier are A, B, C, and multiplier operator is multiple symbol and add operator is the plus symbol. And here we can state that it is a postfix notation. Okay, the second string given is xy plus z in multiply operator. Here the whole term is represented as an expression. Then it is also represented as a term. It is further divided into factor, and a multiply operator. That is in the operator in the last, and factor are xy and plus z. Expression here is for factor is here further divided into expression, then factor, then a multiply operator. Expression is further divided into term, then an add operator. Term here are x and y, add operator is plus, factor is z and multiply, and and last it is multiply operator. At last it is factor and factor, add operator, then again factor and multiply operator, and at last it is converted into an identifier, then an add operator, again an identifier and a multiply operator. Here the identifiers are x and y, add operator is add symbol, identifier, and again multiply operator is the multiply symbol, and we can state that it is a postfix notation. Yeah, so the fourth sub problem is wxyz minus and a multiply operator. Here the whole is expression, and according to the previous question we can also further divide it into a factor, then identifier, and we can see that it is also a postfix notation. Okay, now let us proceed to question number 9. Question number 9 states that we have to use Backus-Naur form to describe the syntax of expression in infix notation, where the set of operators and identifier is the same as in BNF for postfix notations, but parentheses must surround expressions being used as factors. For each of these strings, determine whether it is generated by the grammar for infix expression by it or not. If it is, find the steps used to generate the string. Okay, so let us proceed with this question. So we have given some strings as a sub problems. The first string we have is a divided by b plus c divided by d. The whole string is represented as an expression. Divided by b is a term, and then in between there is a add operator, and at last again there is a term. Then further dividing it into factor, we have a then a divide operator and a factor. Again we have add operator, factor, and then again divide operator and again factor. Then further divided into an identifier here is a and b, and in between there is a division operator. Then in between there is the add operator. Then again identifier is c and d, and in between there is a dividing operator. So we can say that it is an infix notation according to b and f. Now the second sub problem we have is the m into n plus p into d plus m minus n plus p minus q. So similar to the prior question, we can state that it is also an infix notation by further divided the expression into the term, then factor, and again into the identifier, and we can say that it is a infix notation. The third and the last string given is m plus n into p minus q. We can see that it is whole as expression. The term are m plus n. In between there is a multiply operator, and again the term is p minus q. Then further dividing the expression into factor, and at last we would divide it into an identifier. The identifier would be m and n, and in between there is a plus operator. Then it would followed by a multiply operator. Then again the identifier would be p, and then in between a subtract operator, and at last q would be an identifier. So it is a infix notation. So now let us proceed to some important question. I hope you are getting it till now. We will now address some more important question in theory of computation. So the question number 10 states that we have to construct a FA, that is finite automata, a PDA, that is the push down automata, and a TM, that is a Turing machine, to accept all these sets L of all strings over 0, 1 ending with 0, 1, 0. According to the question, we have to design all these three machines according to the given criteria. So let us first design the finite automata according to the given criteria. The given diagram on the screen represent the state transition diagram, where q0 is the initial state and q3 is the final state, that is state with double zeros. And from traveling through the initial state to the final state, we are again and again changing the state of the machine, and we will gain the finite automata as per the machine. Okay, so next we have to construct a PDA, that is a push down automata. In push down automata, we should have all these five transition state, that is q0 is the initial state, q1 is the state for reading 0, q2 is the state for reading 1, again q3 is the state for reading the second 0, and q4 is the state for accepting, that is the final state of the FDA. Here the alphabets are used, input symbols are 0, 1, and stack symbols are 0, 1, 2. Here we are using stack symbols because in PDA uses a stack or a heap to store the symbols in the machine. And the transitions from q0 to q4 are further divided from q0 to q0, then q0 to q1, then q1 to q2, and q2 to q3, and then q4 to q4. All these transitions are given on the screen. And here we have some important aspects of the PDA. You can see it on the screen. Okay, so third we have to construct a Turing machine which should have all the state from q0 to q5, that is all the 6 states. q0 is the initial state and q5 is the state for rejecting, that is the final state. In between there are states that are reading 0, 1, and the reading 0 after 1, and again reading second 0 after 1. Alphabets that are input symbols used as 0, 1, and tape symbols, that is 0, 1, 0, where UI is the blank symbol. Here are the transitions of the Turing machine from q0 to q5 and all the in between states of the Turing machine. You can see it on the screen. Here are the transitions of the Turing machine from q0 to q5 and all the in between states of the Turing machine. You can see it on the screen. Okay, so now let us proceed to the question number 10th. Question number 10 states that we have to construct a Turing machine that accepts the languages 0 1 multiply plus 1 0 multiply. Turing machine will generate an output regardless of the fact that the output is correct or not. Here we have the state transition diagram from the initial state to the final state, where Q0 is the initial state and Q5 is the final state. And you can see in the diagram the changing of 1 to 0 and again 0 to 1 in the state transition diagram, and this is how the Turing machine works. Okay, so now let us proceed to the next question. The next question is question number 11th. We have to construct a PDA. PDA is push down automata equivalent to the following CFG. The CFG is given in the question. We have to test whether 0 1 0 to the power 4 is in the CFG or not. Okay, so now let us proceed to the answer of the question. Here we have given the steps to produce push down automata. To construct a push down automata equivalent to the given CFG and test whether a string is in the PDA will follow these steps. The given steps are on the screen. Please follow all these steps to convert the PDA into the CFG. Here we can see all the transitions in the PDA from Q0 to Q3 and all the transitions in the between. Okay, so last we have the steps to test whether 0 1 0 is in the CFG or not. So please follow all these steps. At last we can conclude that since the PDA reaches the accept state Q3 after processing the input 0 1 0 and emptying the stack, 0 1 0 is the language of the PDA, which means it is the language generated by CFG. And here we are at the end of the video. Thank you for watching.